As speaker, Dr. Neeraja Sahasrabudhe from Department of Mathematical Science and the Institute of Science Education and Research. Dr. Neeraja is currently working as an assistant professor at the Department of Mathematical Science of Indian Institute. Prior to joining Mohali, she spent some periods as a postdoctoral researcher at the Indian Statistical Institute and the Indian Institute of Technology, Bombay. She finished her PhD thesis from the University of Padova, Italy. Her research interests are mainly in the areas of random processes with reinforcement. In particular, she works on linear models, consensus on networks, stochastic approximation, and preferential attachment random graphs. Dr. Neeraja talks about interacting polyhedrons and network applications. Please, you can start, Doctor.
Thank you. Thank you so much for inviting me to give a talk as part of this webinar series. So I'm going to talk about interacting on processes. Well, it should be interacting on processes, I'm sorry. And is it okay if I switch off my video because the internet connection, I mean, I got disconnected earlier, so I'm a bit worried about that. And the voice was getting cut. So. Okay. So, I'll talk about interacting on processes. I'll introduce what interacting on processes are. And then I'll talk about my joint work with Dr. Gulshan Kaur, who is also there, I think. She's also joined the meeting. And please interrupt me if you have any questions in between. That's totally fine. So let me start by saying a bit about UN processes. So UN models fall under this large class of problems known as random processes with reinforcement. And classically, UN models have been used to model clinical trials, but more recently, they have been used across various problems in opinion dynamics and reinforcement learning and so on, and even to understand ant walks on graphs and so on. Okay, so I'll start by introducing classical learn processes. So the first most classical learn process, known as the Polya model, was introduced by George Polya in 1923. So what is this process? So you start with an urn which contains a finite number of balls of different colors. So we are going to stick to 2 colors only throughout. I will mention a few general definitions about finitely many colors, but mostly we are going to stick to 2 color urns. Okay. So at every time step, you draw a ball from the urn uniformly at random and then put it back along with a ball of the same color, or you put it back along with A balls of the same color, okay, where A is some positive number. Okay, so pictorially, this is what is happening. Let's say you have 2 blue balls and 1 red ball. If you started with something like this, and in the next step, if you drew a blue ball, then you put it back in the urn with another blue ball. Okay? So it proceeds something like this. So if you started with 1 white, 1 black, so I'm actually going to stick to white and black. I'll just call the 2 colors white and black. So if you started with 1 white, 1 black, the possibilities are that if you draw white in the first step, with probability half now, because you have only 1 white and 1 black, in the next step, you will be at WWB, or if you draw black, then you will be at WBB, and so on, right? So there can be these many different paths if you keep doing this. So the question is, what happens as time goes to infinity? And this was answered by Polya in 1923. So if ZT is the fraction of white balls in the urn at time t, then the most well-known result on Polya urn is this, which says that ZT converges to a random variable Z, which is distributed as beta distribution as time goes to infinity, and it converges almost surely to this random variable. So just to go back to this picture all we are saying is, what we are asking is what happens to the composition of the urn as time goes to infinity. And this is telling us that the fraction of balls of white color, and therefore also the fraction of balls of black color, because that is just 1 minus ZT. So the fraction of balls of either color converges to a random variable, which the distribution of that random variable is known, and it is beta distribution with the parameters which are given by the initial composition of the urn. So Z0 is the initial number of fraction of white balls in the urn.
Please, T is an integer number here, not real number. The small t, the small t. Z
small t is time, and it is discrete. So at
discrete
time one, yeah, the process is discrete, in discrete time. So all the processes that I'm going to define are in discrete time. So T is just the time. So ZT is the fraction of white balls in the urn at time T. And then I'm taking T to infinity. Okay. So there are, of course, extensions of this model that people have studied. Some of the common ones that I'm going to describe here is, the first one is Friedman urn. So now in the Polya urn, every time a ball is drawn, you add balls of the same color. In the Friedman urn, when you draw a ball of, let's say, white color, you add A many balls of the white color and B many balls of the black color. So you're adding balls of both colors to the urn. It's just that the number is different. So when you draw white, you add, let's say, alpha many white and beta many black. If you draw black, then you add alpha many black and beta many white. And the nature of the asymptote, that this ZT, the way it behaves,
recording in progress,
that changes significantly in this case. So in this case, we saw that ZT was going to a random limit. Here, ZT goes to 1/2. So no matter what you start with, of course, you should start with non-zero number of balls of either color. Well, eventually you are going to add balls of both colors, so it's not going to matter. But even if you start with a very large number of white balls and very small number of black balls, eventually things will even out, which is a very interesting phenomenon. And then, of course, one can generalize this. Yes.
Whatever the value of A, B, and B, the
they have
limit
to
is constant.
Yeah, constant and positive.
Okay, thank you.
So a very simple generalization of this is Bakchi-Pal urn, where when you are drawing a white ball, you add A many white balls and B many black balls. And if you draw a black ball, then you add C many black balls and D many white balls. Okay. In that case also, the limiting fraction is deterministic. So it converges to C over B plus C in this case, and so on. So let me describe a way of writing. I believe that it's difficult to grasp the way I have written these models. It might be difficult to immediately grasp what is happening. So let me give you a very simple way of writing an urn model scheme. So a K color urn process containing balls of K different colors can be just represented by a matrix, right? So I have this K cross K matrix where Ri jet element represents the number of balls of color J added to the urn if ball of color I is drawn. Right? So if I draw a ball of color I add Rij number of balls of color J. So in this notation, now I can write my Polya urn as, so all of these will become 2 cross 2 matrices because I'm talking about only 2 color urns. So Polya urn, this R, which I called reinforcement matrix, it is also known as replacement matrix in the literature. So for the Polya urn, it becomes a multiple of identity matrix, because if you are drawing white, you are adding A many white and 0 number of black. And if you are drawing black, you are adding 0 number of white and A many black. Friedman urn becomes alpha, beta, beta, alpha, because if I'm drawing white, then I'm adding alpha many white and beta many black. And if I'm drawing black, then I'm adding beta many white and alpha many black. Okay. And in case of Bakchi-Pal urn, it is just ABCD with A plus B equals C plus D. So this is what I meant by the urn being balanced. So I mentioned here that the urn is balanced. That just means that the row sums are same. Okay, what does it mean to say that the row sums are same? It just means that you are adding the same total number of balls in each step, right? So if I draw white, I add A many white and B many black, and A plus B is the total number of balls that I'm adding in that step. Similarly, if I draw black, I add C many white and D many black, and C plus D is the total number of balls that I'm adding at that step. Okay. So A plus B equals C plus D ensures that I am adding the same number of balls at every step. And the total number of balls in the urn is growing linearly. So these are some of the, yes.
And all the parameters are non-negative. Yeah, you cannot
yes,
remove balls.
Well, you can. There are processes where you look at also removing the balls, like O'Keill process and so on. But I'm not talking about that. So everything is positive.
Okay.
So I'm only going to talk about urns where you add balls to the urn. All right. So other than the limiting behavior, there are other things that people have looked at. So for instance, there is this well-known...
The Friedman urn is a specific case of the last one.
Friedman case is a specific case of the Bachipal urn. That's right. Yeah.
Okay.
If you make, so if I just go back here, if B plus C, if B and C are same, then it just becomes 1/2.
Okay. Thanks.
All right. So the other kinds of things that people have looked at, I just want to show an example of another classical result, which was proved by David Friedman. There's a different Friedman than the one who came up with Friedman urn in 1965. So what does this say? So we know that ZT converges to 1/2 as time goes to infinity. Now this result is a sort of scaling limit CLT type of result, which tells you about the fluctuations around the limit. So we are looking at ZT minus 1/2. We know that ZT converges to 1/2. So if you appropriately scale it, this converges in distribution to a Gaussian with mean 0 and the variance given by rho square over 4 times 1 plus 2 rho. Okay, where rho is alpha minus beta divided by alpha plus beta. Remember, alpha and beta are the parameters of the Friedman urn. Similarly, for rho equal to 1/2, the scaling changes to square root of t over log t, and the variance changes to rho square over 4. Okay, so I just want to point out a couple of things here. One is that I have not said what happens for rho greater than 1/2. In that case, the limit is not Gaussian, although that result is discussed in this paper, but I just want to focus on these two for now. And I also want to say a little bit about what is this rho. So if we go back to this replacement matrix, alpha, beta, beta, alpha, you realize that alpha minus beta and alpha plus beta are both eigenvalues of this matrix. So the behavior of these urns depends crucially on the spectral properties of this replacement matrix or the reinforcement matrix. In fact, if I were to scale this matrix by alpha, so if I divide each term by alpha plus beta, then the row sum becomes 1. So 1 becomes an eigenvalue, and alpha minus beta becomes the smaller eigenvalue, right? So rho will just become alpha minus beta. Well, it will be alpha or alpha plus beta minus beta or alpha plus beta, but the scale matrix will have this as the smaller eigenvalue. This is something that is observed in urn processes, and I've said this here also, that the asymptotic properties of the urn depends on the spectral properties of this reinforcement matrix R. Another reason why I'm showing you this result is because I'm also going to talk about generalization of this result and of course of the convergence result shown earlier. So these are some of the very classical results known for single urns, and people have looked at. So I've given you three basic examples of urn processes. People have, of course, looked at various kinds of extensions of these models. So here are some of the extensions and some of the people who have looked at it. I'm sure I have missed out several names because it's a very active area of research now. So one of the extension is in the direction of multicolor urns. So I spoke about, yes.
What is the condition answering the positivity of rho.
Yeah, you need alpha. Well, yes, that is something.
You suppose that alpha is larger
yes,
than beta.
yes,
Okay.
you can assume it.
Okay, thanks. Is the ratio between the two eigenvalues of the replacement
Yes.
of the matrix R? Okay. Thanks.
Yeah, if you look at the eigenvalues of this, it is going to be alpha minus beta and alpha plus beta. All right. So so the immediate thing, because I'm talking about two color models, one could look at k color models and look at similar properties of what happens as time goes to infinity to the fraction of balls of each color. And people have worked on this. Then there has been a lot of work on multiple drawings. So in the models that I described, we are drawing one ball at a time, observing the color of the drawn ball and putting back balls based on what we have drawn. But what you can do is you can draw a sample of S balls, and then depending on how many whites are there and how many blacks are there, you can put back a multiple of those. Right? So it would be a multiple drawings model, which people have again, Professor Hosam Mahmood and Marcus Kuba have looked at this sort of models. Then there have been infinite color urns and also random replacement urns. Where so by random, I guess it's clear by what I mean by infinite colors, but let me explain what I mean by random replacement. So these replacement matrices right now, I'm fixing these A's and alpha betas and B and C's. So these are some fixed numbers. Instead, you can take them to be random variables. So at every time you add a random number of balls to the urn. Okay. So that is what I mean by random replacement. So people have also looked at random replacement urns and so on. So these are various directions in which people have taken this area into. I am going to talk about a specific direction where I have worked a bit, which is called interacting urns. So let me explain what I mean by interacting urns. So now instead of looking at one urn, I have n urns. And the reinforcement in each urn now depends on a non-trivial subset of these urns. So what do I mean by that? So if I have, so earlier I had a single urn, I was drawing from that urn based on whatever I saw, I was reinforcing that urn. Now I have n urns, I draw from all the n urns independently, let's say, but what I add depends on what I see in the drawn sample across urns. Okay. So again, I'm going to restrict myself to two color urns and balanced urn schemes. So let me describe the model a little bit more in detail, and I'll also fix the notation now. So capital N is my number of urns, and WIT and BIT is the number of white balls and black balls in ith urn at time t. So I have to also index by urn now. Okay. So what I mean by this interaction is that the number of balls that you are adding at time t, which here is my IIW and IIB, is going to depend on other urns as well. Okay. And like I had mentioned earlier, we are only going to add balls to the urn. So this reinforcement is non-negative and finite. Okay. So if the evolution of or the reinforcement in ith urn depends on some I1, I2, IKI urns, so that I would call the dependency set of this ith urn. But I'm going to look at graph-based interactions. So this will all this will simplify very soon. But before I get to the graph-based interactions, I want to talk about other models that people have looked at. So the first model that I want to talk about interacting urns, this was studied by Daipra, Minelli, Lewis, and Grimaldi. So this is two of their papers. So one is about convergence, the other is about fluctuation theorems, just like I showed you two results earlier. Okay.
Could you please explain the I variable, because in the
yes.
last slide we have 2 coordinates and 3 coordinates. It's we have some trouble in the definition.
Okay, yeah. So once I describe the model, it will be more clear. So I'm going to describe a more specific model now, so that will be more clear, and then I can go back and describe what I mean by.
Okay.
So this model, you have n 2-color urns. Okay. Now at each time, let's say at time 0, each urn contains non-zero number of white, non-zero number of black balls. Okay. Now at each time, you draw a ball, you add a ball to ith urn with probability alpha zt plus 1 minus alpha zit. Now let me explain what this is. Zit is the fraction of white balls in ith urn, and zt is this overall fraction. So you're just taking average of the fraction of balls in all the urns. So this is where the interaction with all the urns is coming in. So earlier, remember when you had a single urn, you were drawing uniformly at random. We are not doing that anymore. We are adding a new white ball in the urn at time t with probability alpha zt plus 1 minus alpha zit, where alpha is some parameter. Alpha is a fixed parameter.
The second step is applied on each arm I, or I is chosen randomly?
No. So you do this across urns simultaneously. So for each urn, we do this.
Okay. For each arm. Okay.
Yes. Simultaneously for each urn, a new white ball is added with this probability.
Okay, thank you.
Okay, so I'm just going to show you what all they showed, because I want to get to the graph-based interaction as well. So here is what all they showed. So remember, this is sort of Polya type interacting models, because at one time you are adding either a white ball or a black ball. Okay? That is what was happening in a single Polya urn as well. So at any given time, you either add a white ball or you add a black ball, but never both colors. Okay, so what did they show? They showed that ZIT, sorry, this should be T going to infinity. So ZIT converges to a random limit Z, just like in the earlier single Polya urn case. But the distribution of this limit is not known in this case. So in the single Polya urn case, the distribution of the limit is known. It is beta distribution. In this case, it is not known. And they also showed corresponding fluctuation theorems, which are here and here, very similar to what we saw for a single Friedman one. The scaling is also very similar. Are there any questions? So in this case, the scaling depends on this alpha, this interaction parameter alpha. All right. So just like these interacting Polya urns, one could study interacting Friedman urns, which is something that I did, and parallelly there was another group which was working on the similar problem. So here in this model, instead of saying that you add one white ball with this probability, I can say that you add alpha many white balls and beta many black balls with this probability. Right? So it just becomes a generalized version of this. It becomes an interacting Friedman urn model. Okay, so in that case, one can again show similar things, that the urns, all the urns actually go to the limit 1/2. And additionally, one could also show this, I could also show this fluctuation theorem, which you notice is exactly similar to what Friedman had got in 1965. If I put n equal to 1 here, I get the same thing. Okay, so from this interacting Friedman urn model, one could get the results for a single Friedman urn as well. All right, so now just to go back to this model and look at how the interaction is happening. So let me just again recall. So the interaction is happening in the following way. Each urn is updating based on the fraction of white balls in that urn at that time. And it is also looking at the overall fraction or the average of the fraction of white balls across urns. right? Which is this ZT, which is just the average of the fraction of white balls in all the urns. Okay, so in some sense, each urn is looking at itself and also interacting with all the urns in the system. Okay, but we don't want to do this. This is like having having everyone interact with everyone. Okay, so we don't want to do this. We want to add. Sorry, is there a question? Okay.
No.
So we wanted to study slightly more interesting model where, let's say, in this case, I would say that the underlying graph is complete because everyone can interact with everyone. We wanted to study it on a non-trivial graph structure. So that is the problem that I am going to talk about in detail. So interacting urns on finite directed graphs. So what do? We fix a directed network or a directed graph with n nodes, and E denotes the set of directed edges. Okay. So at every vertex, I'm going to place an urn, and now the urns are going to only interact with their neighbors. Okay. Now, based on how my graph looks, I divide the vertex set of the graph into two disjoint sets. The first one is the vertices of degree 0 in degree 0, and the other one with non-zero in degree. So I call these stubborn vertices and flexible vertices, and it'll be clear why I'm doing this in a bit. But I'll just give you all the assumptions right away. So we also say, assume that there are no isolated vertices in the graph, and there are no vertices with only a single self loop, which is also in some sense isolated. It's isolated from all the other vertices. So we don't look at these two cases.
Please, can you redefine the definition of a degree of a node?
Yes. So since it's a directed graph, there are two types of, there is in degree and out degree. So let me just go to this picture and then it will be easier. So if we look at the vertex 3, it has out degree 2 and in degree 1, because it has one incoming edge and two outgoing edges. Okay. So each vertex has certain in degree, certain out degree. If you look at the vertex 7, it has 0 in degree. No arrow is coming into it. So this is what I call stubborn vertices. Okay. Any vertex with 0, so 7 is the only stubborn vertex in this example. There is 0 in degree, there is no incoming arrow at 7. Okay, so I'm going to look at the reinforcement happening in the direction of the arrow, which is why I call 7 as a stubborn vertex, because there is no reinforcement that is coming into 7. It can influence or it can reinforce the urn at vertex 6, but it will not get reinforced by any of the vertices in the system. Okay. So the vertices with 0 in degree are stubborn. The vertices with non-zero in degree are flexible because they are flexible to change their composition. All right. So, I mean, this is just a mathematical definition of what S and F are. So S is the set of stubborn vertices where the in degree is 0. So D in I denotes the in degree of vertex I. And when D in I is strictly greater than 0, that is, those vertices are called flexible vertices. Okay, so now I'm going to number my vertices. So 1 to F or 1 to mod F are my flexible vertices, and rest of them are stubborn. Okay, just like here. So
can we say that S corresponds to the transient states and F to recurrent states for Markov change?
Well, actually, for S, I mean, I don't know what Markov.
According to this graph,
yes,
we cannot stay in, on state 6 or 7, but
yeah, but I'm not going to think of. I mean, I'm not going to look at a process which is like a Markov chain on the graph. In fact, what will happen is that the urn at 7, that will remain constant throughout.
Okay, thanks.
Because it's not going to get reinforced. Okay. So the last thing, I mean, there's a bit of notation here that I have to introduce to be able to write down the model properly. So once I have labeled my vertices like this, I can write my adjacency matrix of the graph. So remember, the adjacency matrix has entries Aij, which is 1 if I has an edge pointing to j and 0 otherwise. Okay, so that looks like something here, then 0, then ASF here, and then 0. That's because the stubborn vertices, so there are no vertices that are pointing to stubborn vertices. Therefore, this last part becomes 0. Okay, so this is about the graph the underlying graph that I'm going to consider. Now about the reinforcement dynamics. So like I said, that at each vertex, I'm going to place an urn that contains balls of 2 colors, white and black. WIT again is the number of white balls in urn I at time t, and BIT is the number of black balls in urn I at time t. Okay, so now what do? A ball is selected uniformly at random from all the urns simultaneously and independently. Now, based on what you have drawn, each urn is going to reinforce its neighbors. Okay, it's going to reinforce its out neighbors. Okay, according to this matrix. So what do I mean? So if the ith urn, if in the from the ith urn you drew a white ball, all the out neighbors of the ith urn are going to get alpha I many white balls and mi minus alpha I many black balls. If you drew a black ball from the ith urn, then all its out neighbors are going to get mi minus beta I white balls and beta I black balls. Okay, so just to go back to the picture. So from the second urn, if you drew a white ball, 3 will get reinforced according to the matrix I showed you. Okay. Similarly, if from 5 you drew a white ball, 2 will get alpha I many white balls and mi minus alpha I many black balls. So the urns are reinforcing their out neighbors. And therefore, urn 7, which is a stubborn vertex, so which is an urn at a stubborn vertex, is not going to change its configuration at all. It is going to influence the urn at vertex 6, but it is not going to get influenced by any other urn because it has no integrity. Okay. So now we are going to classify the reinforcement in 2 ways. So the first one is what we call Polya type reinforcement. So if this reinforcement matrix becomes a multiple of an identity matrix, which is the classical Polya process, we call this reinforcement Polya type. We call it non-Polya type otherwise, but we have this condition. This is just a technical condition that alpha I plus beta I has to be strictly greater than 0 and strictly less than 2mi. Again, just to recall, I'm only looking at adding balls to the urn. So alpha I is less than mi, beta I is also less than equal to mi. So alpha I plus beta I has to be less than equal to 2mi. We are just looking at the case when it is strictly less than 2mi and strictly greater than 0. So these are the 2 types of reinforcements that we are looking at. Okay, so the question remains the same. What can we say about the limiting fraction of balls of color white in each urn? So now your question is just slightly more complicated because you have n urns and you want to know what happens to the fraction of balls of white color in each of the urns. Okay. So while we do have some results for this case, remember so here my reinforcement depends on the urn, right? I'm looking at Ri. I'm saying that if from the ith urn you draw a white ball, you add alpha I many white balls and mi minus alpha I many black balls. Right? So these things depend on I. So what I'm going to present today is a simpler case, the results from a simpler case that we have studied earlier. And this work is still ongoing, but we do have some interesting results here as well. But I'm just going to also, for the simplicity of notation, I'm going to talk about the case when this does not depend on the node. Okay. So now, if you draw a white ball from on I, all the out neighbors will get alpha many white balls and m minus alpha many black balls. Does not depend on the on. Okay. So either the reinforcement on the whole graph is polar type or it is non-polar type. Okay. So earlier you could have cases where some of the vertices are reinforcing according to polar type, some are reinforcing according to non-polar type. I have simplified that now, and either the reinforcement across all urns is polar type or it is non-polar type. So that is the case that I'm going to talk about. Okay, so now I have to tell you what happens to the fraction of white balls as time goes to infinity. So this is the result that says that under two conditions, you get a deterministic limit. Remember earlier cases when we saw polar type reinforcement, there was always a random limit. Right? So in this case, we have classified when the limit is deterministic. In the examples that I showed you earlier for the single urn models, the limit was deterministic for Friedman urns and for Bakchi-Pal urns. For Friedman urns, it was rather simple. It was just 1/2. All right. So what are these two conditions? So the first condition is that the reinforcement is of non-polar type. And the second condition is that there is at least one stubborn vertex whose influence is reaching to every flexible vertex. Or in other words, that for every flexible vertex, there is a stubborn vertex whose influence is reaching to that flexible vertex. So by this S curved F, I mean that there is a path of directed edges from S to F. Okay. So in that case, we get that this vector, which is where Z1t is the fraction of white balls in urn 1, Z2t is the fraction of white balls in urn 2 at time t, and so on. So I'm looking at this vector now because I'm interested in what is happening as time goes to infinity across urns. Then this Zt has a limit which is given by this Z star, small Z star here. So Zt converges almost surely here under these two conditions. And of course, I have to say here, I have written ZFT because only the composition of flexible urns is going to change. So if I go back to the picture here, like I said, there is going to be no incoming reinforcement at vertex 7. And therefore, the composition of this vertex, the urn at this vertex is not going to change. So I'm only interested in knowing what is happening to all the other urns as time goes to infinity. This one, I know what is going to happen. It is going to remain same as we started at t equal to 0. So number of white balls and number of black balls in this urn is going to remain same as it was at time t equal to 0. Everything else, which comes in F, which is the set of flexible vertices, I'm interested in what happens to them. And this is what happens to them. It goes to this limit. Okay. So just to show you a picture, another graph. So the first graph that we saw is, so the first graph here is the same one that we have seen earlier. So there is a stubborn vertex there. And if you see, the influence of stubborn vertex is reaching everywhere, right? So if you look at 5, you can go from 7 to 5 via 6, 4, 1, 2, 3, and then reach 5. So the influence of the stubborn vertex is reaching everywhere. Therefore, this is going to have a deterministic limit. Okay. The second one, there is no stubborn vertex. Okay. So if the reinforcement is non-polar type, there is going to be a deterministic limit given by Z star. If the reinforcement is polar type, then we have not said anything so far. So we have two cases covered. One is when the reinforcement is polar type, or if you have a stubborn vertex whose influence reaches everywhere, let's say, or if you have more than 2 stubborn vertices. The point is that every flexible vertex should have a stubborn vertex whose influence is reaching to this flexible vertex. Okay, so in the second graph that I have drawn, if the influence becomes Polya type, this result does not tell us anything. Okay, so I am going to talk about what happens in that case. But before that, I want to quickly also say a few more things. So if you look at this Z star, it gives you the final, the limiting composition of the on 1, 2 up to F, right? Now, we also wanted to see under what conditions will this limiting fraction be same across all urns, right? So for that to happen, what should happen is that similar sort of reinforcement should happen in every neighborhood, right? So it would depend on how the reinforcement behaves and how the graph structure is. So under these two conditions, so this essentially means that so Z as 0 is the initial fraction of white balls at stubborn vertices. So this is a vector. Okay, and remember AF I had already defined. So this is this AF, A tilde F is AF times DF inverse, which is the inverse of the degree matrix. Okay, so anyway, I don't want to get too much into the technical conditions. So under these conditions, what we get is that the limiting fraction of white balls across urns is same. Okay, which is given by this 1 minus B plus A plus B minus 1 C1 divided by 1 minus A plus B minus 1 C2. Okay, where C1 and C2 are some constants, and I mean, they come from this condition. If this condition is satisfied, then across all flexible urns, the limiting fraction of white balls is going to be same. Okay. And then we can add a special condition, which is when the reinforcement is non-Polya type and there are no stubborn vertices. Remember, if there are no stubborn vertices, to get a deterministic limit, the reinforcement has to be non-Polya type. And when there are no stubborn vertices, the limit reduces to 1 minus B, 2 minus A minus B. All right, so this just comes as a corollary of the earlier convergence results. So since I don't have time, I was planning to just show how to prove these things, but maybe it's better to discuss the results that we have. And because I have left out the Polya type reinforcement case, I would like to talk about that also. So let me skip the proof method, but let me tell you about the fluctuation theorems and what happens when the reinforcement is Polya type. Okay. So before I go to fluctuation theorems, very quickly, I just want to define something. So because I've not talked about H function, let me go back there. So the main idea of the proof is to write down a recursion for the number of white balls in on I at time t plus 1. Okay, so that one can do by just writing this ZI plus 1 is just number of white balls at time t plus 1 divided by total number of balls, which is nothing but number of white balls at time t plus whatever you are adding, right? And whatever I'm adding, I am denoting by y. So you are adding, sorry, whatever I'm adding is just alpha times whatever you are drawing from the neighbor, right? So this is the sort of thing that you can write by just the definition of the model. Right? So you're adding alpha many white balls if you are drawing a white ball from a neighbor J. That is what this represents. And you are adding M minus beta white balls if you are drawing a black ball from the neighbor J. Okay? And this therefore can be written as a vector valued recursion. So remember, this is for on I. And then I can write for every on I can write this, and then I can write it for the vector ZT, which is this vector of size F. Okay, and this is what it looks like. Okay, so fraction of balls across urns 1 to F at time t plus 1 is just fraction of balls across urns 1 to F at time t plus all of this. Okay, this comes from the reinforcement part. Okay, and now this can be written nicely as a martingale difference and some function h. And this function h becomes important in determining what are the limit points. Okay. So it becomes important in determining the limiting point z star that we saw earlier, and it also becomes important in determining how the fluctuations will happen around the limit. Okay, so this h function, if you notice, which I have written here, depends not only on the initial condition of the stubborn vertices, but also on the adjacency matrix. Okay, so it depends on adjacency matrix, it depends on the initial condition of the stubborn vertices, and finally it depends on A and B, which are coming from the reinforcement matrix. Okay, so it has all the information about the kind of reinformation you are doing and the kind of graph that you are working on. Okay, which is not a surprise because the limiting behavior should depend on these two things. Okay. So now I look at the Jacobian of this, okay, and I look at the minimum eigenvalue of this Jacobian. Why I want to point this out is because remember when we looked at single urns, I said that the limiting properties of the urn depends on the spectral properties of the replacement matrix. Now, when we look at interacting urns on a graph, it seems that the limiting behavior depends on the spectral properties of a matrix, which depends on the graph as well as the replacement matrix. So these A and B are the elements coming from the reinforcement matrix. This A tilde F is the part coming from the adjacency matrix of the graph. Okay. So now these limiting properties of this system depends on the spectral properties of a matrix, which depends on both. Okay, so now I define rho as the minimum eigenvalue of H, and this is what we get. So this is slightly complicated. So this is the fluctuation theorem, the corresponding fluctuation theorem. So when rho is greater than half, I get, again, if you notice, the scaling is very similar to what we got earlier. The scaling is just root t, and then we are looking at ZFT and its fluctuation around the limit z star, and it simplifies in cases when you have symmetry in the graph, right? So this is the second point where I've written A tilde is A tilde transpose, which means that your scaled adjacency matrix is symmetric. In that case, the limiting variance simplifies quite a lot. Similarly, for rho equal to half, I can write down a fluctuation theorem with the same scaling that David Friedman got in 1965. So root t and square root of t over log t.
Equation 2 converges to normal 0.
Sorry, it's 0. Yes, it's normal 0 and sigma tilde. Yeah.
Okay.
Sorry for the type. Okay. And again, when your scaled adjacency is symmetric, you can simplify the limiting variance, and it actually looks quite nice in this case. Okay. So before I move to the Polya type very quickly, because do I have just like 5 minutes maybe to talk about Polya type?
Yes, 5 minutes.
Yeah, I'll finish 5 minutes. Okay. So before that, I just want to recall some of the things that we have said earlier and connect it with that. So I would call this Friedman type reinforcement when A is equal to B. And in that case, you will, if you go back to the result, the Z star actually becomes 1/2. So if my reinforcement was not just non-Polya type, it was in fact Friedman type, I will get back the classical result of the Friedman urns, which is that ZFT converges to 1/2. And further, in the fluctuation theorems, some of these things will simplify. This CAB, which is just a constant, which is multiplying in various places in the variance, it appears in the limiting variance, also simplifies significantly. It just becomes a minus half whole square. Okay, so while we started with a much general setup, once you come back to the special cases and you know what the original results are, you can see that they are really matching with the original results. Okay, and finally, because earlier also when I stated David Friedman's result, and here as well, I have only looked at rho greater than half and rho equal to half case, and I said that rho less than half case I will not talk about. So I will just make a remark here that in this case, the difference, that ZFT minus the limit, if you scale it appropriately, and that scaling actually depends on rho, it converges to well-weighted sum of some random vectors in this case. So that part is known, but not much is known. It is known that it's not Gaussian. Okay, so let me very quickly tell you what happens in the Polya case. So in the Polya case, what we are going to assume is the following, because we couldn't prove everything for the general case that we started with. So we are going to assume that the underlying graph is connected and it is deregular, which means that every vertex has the same degree. Okay. So now I'm thinking of an undirected graph just to simplify everything, and everything has same degree. Every vertex has same degree. And I'm saying that my A, which is my adjacency matrix, I assume that it is diagonalizable. Finally, I also assume that the initial number of balls in each urn is same. This was not required in the earlier part. So once I have all these assumptions, we could show that ZT, which is the fraction, this vector of fraction of balls of white color in all the urns, this converges to a random limit which is same across all urns. Okay, so what is written here is ZT minus Z bar T goes to 0 almost surely, and in L2, so this Z bar T also converges to a random limit. Z bar T is not a vector. It's the average of the fractions. Okay, so we could show that there is a synchronization in the Polya type reinforcement as well, which means, so here by synchronization, I mean that each urn, in each urn, the fraction of white balls converge to the same random limit almost surely. Okay, so I have defined Z bar here, which is very similar to what was defined by Paulo Daipra and Grimaldi in their paper. So it is just 1 over n sum over ZIT. Okay, and the idea is fairly simple. You can just show that this Z bar T is martingale, and therefore it has an almost sure limit. And then you show that ZT minus Z bar T also has, well, it has an almost sure limit, and that limit is actually 0. However, this uses some more results from martingale theory, which if I have time, I can show, otherwise I can skip.
Analysis has brought to the cost and central of mathematics application for science and
Hello.
Yes, yes.
Is there a question?
No question. Sorry.
Yeah, okay. Okay, so the first part is fairly easy. So should I go ahead and just give you, I mean, it's just 2 slides. I can just give the sketch of the. All right, so you can show that Z bar T is in fact a martingale, and therefore it has an almost sure limit. Then you show that the variance of ZT and Z bar T actually goes to 0 at a rate which is like 1 over T to the something. Finally, you show that ZT admits an almost sure limit. ZT, remember, is the vector of fraction of balls of on 1, on 2, on 3, and on n. Since G is connected and deregular now, there are no stubborn vertices. There are only flexible vertices, and the reinforcement type is Polya type across. Okay, so you show that ZT also admits of almost sure limit. So that we do by showing that ZT is in fact a quasi-martingale. And then finally, you show that this norm of ZT minus Z bar T admits an almost sure limit. And because the variance or the second moment is going to 0, in fact, you can show that the second moment is going to 0. This has to be 0. This has to go to 0. So that's the sketch of the proof. This one we show by using an interesting theorem of Robinson-Sigmund, which I just want to show because I just find it interesting that we are doing this now, and this is an old result. Well, okay, not very old in mathematics, I would say, but it was published in 1976. And if you look at Earn models literature now, a lot of people are using this particular result on what are known as almost super martingales to prove certain things about on processes similar to what we have done, which I find interesting that we go back to results which were proved long back, and I think that's why mathematics is a very interesting area, which is very different from other sciences. All right, so I think I'll stop here. This was the sketch of the synchronization for polyons, which is the part that we had left out in the earlier result. So now we have more or less covered what happens in polyar type, what happens in non-polyar type, except that for the polyar type, I need these assumptions. Okay. Thank you.
Okay, thank you for you, Dr. Najira, for this nice talk and to introduce us the beautiful combinatorial objects. Are there some questions, please?
Yes.
Yes.
Thank you very much for your nice talk. My question is related to the motivation of your work, the motivation of considering many errors on the nodes of a graph. The motivation, is it purely mathematics, or is it inspired from real situation?
Well, the motivation was purely mathematical, I would say, because I was working on that earlier result that I showed with Friedman-Nunz, which was for complete graphs. And then with Gushan, we discussed and we thought, why not make it slightly more non-trivial and look at graphs? We started with undirected graphs, then we thought, why not look at directed graphs? That would be more interesting and more, hopefully, you get more interesting results there. So motivation was purely theoretical in that sense, but we did think about some sort of application, and I think there is more that one can do there, especially in opinion dynamics. So if you think of white and black as inclinations towards a particular topic, positive and negative inclination, the fraction, if you think of it that way, what is happening here is you are influencing your neighbors based on what they see. Drawing a ball is like an instance of seeing one of your views, and based on that, they are getting influenced.
And
so the applications that we thought of.
Can we imagine a situation where the adjacency matrix has no impact on the limiting distribution? Adding some condition on the rule of changing the ball, and because according to the results, the limiting distribution depends on the matrix A. So can we imagine, or as a perspective, how to manage the rule of adding black and white balls to ensure the
well, actually, the Friedman case, that happens, right? It goes to 1/2, irrespective of what the graph is.
Okay. So it is independent of the graph. Okay, in this case, okay.
Of course, I mean, if it's a stubborn vertex, then it will remain what it started with. So I'm only talking about vertices which are getting updated, let's say. Otherwise, there's no point talking about it. So The vertices that are getting updated, if the reinforcement is Friedman type, then it is going to half, irrespective of how the graph.
Okay, thank you.
So if we start our urn by one black ball and 9,000 blue balls, and we use Friedman urns, at infinity we have 50% black and 50% blue balls. Very nice result.
Yes, that's a very interesting. I think that's a first sort of non-intuitive result that one comes across on models, and it's a nice thing to think about. That what is, write down maybe a few examples and see what is few steps and see what is happening.
Yeah. And your matrix, if your matrix R is random, this complicates the situation or not? If we consider R as random matrix, not deterministic matrix.
Yes, that will be. So one of the things that we are looking at is balanced turns. So total number of balls being added. That's why I'm looking at alpha, m minus alpha, m minus beta.
Okay.
So the row sums are m. And that helps me because the total number of balls is linear. And that helps me crucially in some of the proofs. So we have used it crucially in proofs. But once you start adding random number of balls, then that goes away. So you have to handle that also a little bit. It is doable, but you have to handle that separately.
The same thing when R is not deterministic, it's not, sorry, balanced. We same number.
Yes.
It complicates the situation.
Yes. Actually, there is some work on unbalanced terms, but not a lot of work on.
Some other questions, please.
Rafik, I have a question, please.
Yes.
First, thank you very much for this very nice talk. I have a question about the result about central limit theorem, asymptotic normality you get. Do you know something about the rate of convergence in such kind of results? Do you have?
So what do you mean by rate of convergence? Because scaling gives you some sort of rate, right? I mean, this root t.
Yes, you have the convergence of square root of t times z f of t minus z star. And is there some result if you use, for example, the Kolmogorov distance or something like this? If you know something about the rate of convergence, or is there some result about the rate of convergence even in a more simple case?
No, I don't recall seeing anything of that nature.
Okay.
Yeah. I mean, so the other sort of convergence rate one can see is the L2 convergence rate, which is because in this case, the non-Polya type case, the limit is deterministic, right? So if we just look at the vector ZFT, variance of that is going to 0 at some rate.
Okay.
So that sort of rates people have looked at. In fact, in the earlier model that I showed you on complete graph, we have looked at that sort of rates, but not what you're saying. That might be interesting actually to look at, but I have not seen any
result of this kind.
Yeah. No,
okay.
No,
okay. Thank you.
Thank you, Dr. Mohammed Al-Mashkouri. For information, Dr. Mohammed Al-Mashkouri will be our speaker in 24 October, the next October. Inshallah. Okay. Some other questions, please.
Yes, Mayor.
Yes, Doctor.
Alhamdulillah. Good afternoon, everyone. Thank you, Professor Neeraja, for a nice presentation. Professor, are you familiar with the Collatz conjecture, of course?
Collatz conjecture?
Yes.
Yes.
Okay. From at the beginning of the presentation, I felt that there was some parallel between this and the Collatz conjecture when you were picking up the beta convergence. When you because if you think And maybe you can make some parallel with this, because if you try to the number of the blue ball, the black balls, for example, if you pick up the black ball, then if you have an even, then you like pick up half of them, you take out half of them. If you have an odd, then you add 3 times their number plus 1, etc. Maybe you'll have like a physical interpretation, or a physical at least simulation of what happens with the collapse conjecture. And I think in that case, if you can come up with some kind of limit or something, then this would may break at least a window into the collapse conjecture and results. What do you think?
I mean, so you're saying, in fact, one of the things that we had started with is to say that when the fraction of balls is, let's say, greater than something, okay?
Yeah.
But that, essentially what you're saying is that it depends, you look at the composition of the urn, and then you look at the numbers and put some conditions on that.
Yeah,
that
right.
seems like a more difficult problem than just to draw a ball randomly.
I'm
and
sure. Yeah, of course. Yeah.
Because then you don't have to keep track of what is actually happening in the urn. You just draw and take it as a sample of, probabilistic sample, because you're drawing uniformly at random, and then based on that you do something. So
Yeah.
I'm not sure, but it seems, I mean, I don't know if one can really do that, but if one,
Well,
yeah.
I think you're close. I mean, I think some of your results are certainly, are close. You can, the only difference is that there is specific choices. If the number is even, then you divide by 2. If the number is odd, then you multiply by 3 and plus 1. And so it's like there is specific a choice in this case. And the idea is, if you are able to simulate this, at least in one under certain conditions or something, and you come up with some kind of limit, and then this will be like a great breakthrough for this type of mathematics and statistical analysis that you have done. I mean, this is an idea, but
definitely think about it. It sounds interesting, so we'll definitely think about it.
By the way, I wrote to you, and I would like to invite you to my group, and also to the PAM group, and also it would be nice to receive your presentation.
Yes, I saw some of the typos, so I'm going to fix it and then share it. So because
yes, okay. As you wish. Inshallah, I send you the email. Yeah, thank you very much.
Thank you so much.
Thank you, Dr. Fathi, for this nice question. It will be a future research project.
Inshallah. Okay, I'll be happy to collaborate.
Very nice idea.
Get some Gulf or Asian type, Asian African type of results. Okay, yeah. مشكور الله يجزيك خير. شكرا.
Thank you.
Thank you, brother Nabil. كذلك.
شكرا فتحي.
Other questions? Are there other questions, please? So, thanks again, Dr. Neeraja, for this nice talk. Thank you for all the public. Please don't forget to send me your slides to put them in our website.